The first thing you have to ask yourself is what is physics? Um, it's customary for people to think of physics as, something I just can't understand, or, something that's just too complicated. But physics is basically everything around you. So it shouldn't be something difficult to understand, because everything that is around you can be explained by physics. So, in essence, physics is the branch of science which describes nature. So, if you were to just go outside and just observe anything, you can explain that phenomenon with physics. Just anything. You go outside or even inside, you turn your light on, you have electricity, physics. Your refrigerator or whatever you have, physics. You turn your pipe on, water come, physics. You walk from here to there, physics. So everything that you do involve physics. So it's just a branch of sciences that just describe nature. It is the property of matter and energy. Okay, and when we do physics, we will do mechanics, and it's customary to do mechanics first. We do mechanics, heat, light, other radiation, um, sound, electricity, magnetism, and the structure of atoms. So, those are the topics that comprise physics. But basically, on just understanding how the universe works, as simple as that, just understanding how the universe works, that is what physics is. It essentially describes the behavior of everything around you. So don't think of physics as a very complex, difficult, you know, study. So one of the first topics that we're gonna touch on is mechanics. So what is mechanics? So mechanics is a study of motion of objects. You know, any objects. You drop a ball, you roll a ball, you drive a car. So mechanics is the study of motion of objects. So, some of the questions that you might ask yourself is why objects move, why objects stop, why objects change direction. So all of those things are physics principles, you know. Why objects move. I mean, if you apply some type of energy to something, it's gonna move. But why it stop? If there weren't any friction, that object would move continuously. It wouldn't stop at all. Why it changed direction? There must be some additional force which changed the direction of that moving object. So just simple little things like that. I mean, you know, you should question, and by asking those questions, then you can work out, the what's going on. But there is a branch of mechanics we call kinematics that you should have an understanding of kinematics, and later on you will fully appreciate what kinematics is. So I would say the mechanics is, basically why object moves. But kinematics is the science that describes the motion of objects. So you know you can sort of differentiate them. So kinematics is the science of describing the motion of objects. And you have a number of equations. We talk about a set of four equations that you can utilize to predict unknown information about an object's motion if other information is known. So just put that in your back pocket a little bit, and we'll get back to kinematics. But kinematics is very important. All right, so let's move on. I mean, these are the equations that we talk about, but we'll get back to it at some point in time. Not, we don't want to confuse you right now, but these four equations, D is distance or displacement, V is velocity, T is time, A is acceleration. So what we're saying is that if you know, say you know three of these things, if you know velocity, if you know time, and you know acceleration, you can get distance. You know, um, so, and if you're going to use this kinematic equation, if you know velocity and you know time, you can get distance. So it is just a set of equation that if you know some values of, say time and velocity and acceleration, you can get displacement or distance. But we'll get to that at a later time. Now, before we go into mechanics, you have to understand the difference between scalar quantity and vector quantity. Okay? When we talk about a scalar quantity is described only by magnitude, just a numerical value. Okay? So if you say that, you know, he's driving at 20 miles per hour, all you're doing, you're giving a magnitude to something. Okay? So that is a scalar quantity, which is different from a vector quantity. When we talk about a vector quantity, it is a quantity that has a direction associated with it. Okay? So it a vector quantity would be, he's driving 20 miles per hour in an eastward direction. You see? So in addition to the numerical value, you're given a direction now. So that changes that scalar quantity to a vector quantity. So a scalar quantity just describe the magnitude, or if you use a numerical value to describe some motion. Okay? Whereas the vector quantity has magnitude and direction. Very important, magnitude and direction. So if you're going to represent a vector quantity, it is represented by a line, a directed line segment. So you give a line segment moving in a direction. I will show you what that looks like. So if you're going to use a directed line segment, then the length of the segment is going to represent the magnitude, the number, and then the orientation in space of that line segment going to give you the direction. Okay, so if you say somebody weighs 20 pounds, that's a scalar quantity. It has no direction associated with it. But if you talk about a weight and it moving in a specific direction, then that's a vector quantity. So you have to know the difference between scalar and vector quantity. And as I said, with a vector quantity, you can use a directed line segment to represent a vector quantity, because the length of the segment represents the magnitude, and then the orientation in space of that line segment is going to tell you about the direction. So this is what we mean. So so okay, so look at these are some scalar quantity. Length, okay, so if you say, the length of my book is 12 centimeters, okay, that's a scalar quantity. Area, again. So if you say the area of the box is 40 centimeters squared, volume, speed, mass, density, pressure, temperature, energy, entropy, work, power. So these are all things that are represented by magnitude. So these stuff right here only have magnitude. They only have a value which tell you how much of something is going on. Whereas the vector quantity now, in addition to having a magnitude, okay, it's going to have a direction. Okay? So something like velocity, when you hear velocity, it has a magnitude and a direction. So the difference between velocity and speed, velocity has a direction associated with it. Acceleration have a direction associated with it. Momentum, force, when you talk about lift, drag, thrust, and then weight, because the weight is actually, if you think about it, weight is moving, it is the gravitational pull of that object. So it's going to move in a specific direction. And again, we say you can use a line segment to represent a vector quantity, because the length of the line segment. So if we use this as velocity, if we use this line segment as velocity, the length of the segment represents the magnitude of the velocity, and then you can see the arrow points this way. That means it's moving in this direction. So the orientation of the line segment give you the direction. So you can represent vector quantity like this using this directed line segment. Okay? So the difference between a scalar quantity and a vector quantity, scalar quantity have direction. It has direction associated with it. So, a simple thing. So if these are some vector quantity which has both magnitude and direction, you can see that you know this this line segment is moving in this direction, and then this one is moving in this direction. They have the same direction, but you can see that the magnitude is different. This is longer than this. Okay, so they're not the same, even though they're moving in the same direction. They have different magnitude. The direction is the same. And then if you take this example here, they're moving in different direction. They're moving in different directions. So the arrow tells you the direction. Um, they and you can see that B is probably a little bit longer than A. So they're definitely uh, uh, not the same. As a matter of fact, I think they have the same magnitude. So A and B have the same magnitude, but the direction is different. So these two are different. Okay, these two are different. The direction is different, but the magnitude is the same. And then in example 3, you can see that they both have the same magnitude and they have the same direction. So these two are the same. Okay? So this is what we call vector quantity. It has magnitude and direction. So when vectors are represented like this, the length of the line segment, it represents the magnitude, and then the orientation uh, of the line segment give you the direction. So this is a quick example of comparing vectors. All right, they may have the same magnitude but have different direction. They may have the same direction but different magnitude. So you have to understand that, and it's very important to to understand vectors, because when you do a little bit more, when you look into mechanics a little bit more in more details, then vectors comes into place. Again, same direction, different magnitude, same magnitude, different direction. Okay, so let's move on. All right, so again, distance is a scalar quantity that refers to how much ground an object covered during its motion. So we can say, you know, the distance between where I'm sitting and say the pipe is 10 meters. Okay, so that's a scalar quantity because I did not give you a direction. Okay, so it's just how much grounds an object covered during its motion, whereas the vector quantity for distance is displacement, and you have to understand the difference carefully. When we talk about displacement, displacement refers to how far out of place an object is. Okay, and I'm going to show you the difference. So distance is a scalar quantity, just refers to how much ground an, uh, an object covers during its motion. So if I'm going to walk to the pipe and I say it's 10 meters away, I'm going to walk, I'm going to walk to the pipe. But if I say that the displacement is 10 meters, I have to give you directions. I have to give you direction. So the difference between distance and displacement is a vector quantity. Okay? And the best terminology is, how far out of place an object is. That refers to displacement. And this is all right. So let's talk about distance now. All right. Let me explain exactly what is going on. So, all right. Say I am. Say I am. Say I start. Say I'm right here. If I'm right here, okay. Say I'm right here, and I if I walk, say I walk 7 meters, okay, all right, I can walk 2 meters here, okay, and then I can change my direction and then walk 5 meters here, okay, all right, and I tell you what, let's say I walk 14, say I walk 14 meters. For simplicity, say I walk 14 meters. All right, so if I walk 14 meters, and this is the path I'm going to take, I take 2 meters straight up, then 5 meters to the right, and then I go down 2 meters, and then I take 5 meters and come back, and I'm right here. So I walk a total of 14 meters. My displacement is 0 because I remember what we said, displacement is how far out of position you are. But if I travel like this, I am back to square one essentially. I'm not out of place. I am still where I was. The distance I travel is 14 meters. Okay, so the distance is 14 meters, but the displacement is 0.
Okay.
So the reason why the displacement is zero is because displacement takes into consideration directions. So if you want to describe, you're going to say travel vertically, or say, travel straight up 2 meters, then to the right 5 meters, and then downwards 2 meters, and to the left 5 meters, and you end up where you start. Displacement is zero, but distance traveled is 2 plus 5 plus 2 plus 5. So you travel 14 meters because distance does not take into consideration direction, whereas displacement takes direction in consideration. Okay, so that's a very important point that you should try and grasp. All right. So again, the distance from A to A is 14 meters, but the displacement from A to A is zero. Okay. All right. So that gives you a very good um, understanding of the difference between displacement and distance.
Yes.
Displacement is a scale, sorry, displacement is a vector quantity, whereas distance is a scalar quantity. No direction is associated with distance. Direction is associated with displacement. All right. All right. So similarly, when we talk about speed, speed is a scalar quantity. It refers to how fast an object is moving. So you cover X amount of distance per whatever time. It is the rate at which an object covers distance, has nothing to do with velocity, nothing to do with direction, whereas velocity have everything to do with direction. So when we talk about velocity, it is a vector quantity that refers to the rate at which an object changes its position. The rate at which an object changes its position. So if you're going to write the equation for velocity, it is position divided by time, or displacement divided by time, which is different from speed. Speed is just distance over time, whereas velocity, which is a vector quantity, you have to write it as position divided by time, or displacement divided by time. All right? So you have to understand these differences. Velocity is a vector quantity. It has a direction associated with it. Okay? So position divided by time, or displacement divided by time. And similarly, acceleration is a vector quantity. It refers to the quantity. So acceleration is a vector quantity that refers to the rate at which an object changes its velocity. Okay? The rate at which an object changes its velocity. If you're not changing your velocity, there is no acceleration. Okay? So if you're going to write the equation for acceleration, it is equal to velocity divided by time. Okay, so you're gonna get acceleration anytime an object's velocity is changing. If the velocity is not changing, you're not accelerating at all. So if you're driving down the road eastward at 20 miles per hour and your velocity is the same, it's not changing, you're not accelerating at all. So you have to have a change in velocity. Okay, the velocity have to change in order for you to accelerate. Okay, and again, acceleration is a vector quantity. So, you know, when we look at acceleration, you can have what we call constant acceleration. That means the rate at which you're changing your velocity is the same amount each second. So you may be speeding up or slowing down, but the rate at which you're speeding up, you change the velocity by the same amount each time or each second. That's what we call constant acceleration. And we're going to go over this again. Okay? If you're not changing your velocity, there's not going to be any acceleration. But if you're changing your velocity by the same amount each second, then the acceleration is going to be constant. Velocity is changing by a constant amount each second. And an example of that is the acceleration of gravity. You know that gravity pulls objects downwards. Okay, the earth pulls object towards the center. Okay, and it has the gravitational pull or the acceleration due to gravity is 9.8 meters per second each second. So every second, the velocity, if you're falling toward, say you fell off something, you're in an airplane and you fell out of the airplane and you're falling towards earth. Every second, your velocity is going to increase by 9.8 meters per second, right? So when we talk about velocity, velocity is position divided by time. So it is meters per second velocity. But this velocity is going to increase every second. It's going to increase by 9.8 meters per second. And that is what we call constant acceleration. So the acceleration due to gravity is a constant acceleration. And we're going to go over that, so don't worry about that. As opposed to average acceleration. So you have constant acceleration and then average acceleration. When we talk about an average acceleration, what we do, we take the final velocity, initial velocity, and we find the difference between them. So the average acceleration is equal to the final velocity minus the initial velocity divided by time. Because we remember acceleration is equal to the change in velocity with respect to time. Okay, remember the definition for acceleration is change in velocity, and we represent change in velocity as delta v, or delta v, which is change in velocity with respect to time. So if you start with a certain velocity and you finish with, again, you fall out of the airplane. If you fell out of the airplane and you say you start falling at a certain velocity, and you just before you hit earth, you have a certain final velocity. If you subtract from your final velocity the initial velocity and divide it by time, that gives you the average acceleration. Okay, it doesn't tell you what happened in between. It does tell you what happened at the start and what happened at the finish. So that's the average acceleration. Okay, which is different from constant acceleration. but we'll go over that in you know, a little bit more detail. So acceleration, when an object speeds up. So when you say you're driving and you speed up, your acceleration is in the same direction as the velocity, because you're speeding up. So you can only get acceleration if you change in velocity. You can only get acceleration if you change your velocity. So when you speed when an object speeds up in the same direction as the velocity, then we say, you know, sorry, when an object speeds up, its acceleration is in the same direction as the velocity. Because, you know, you can have acceleration opposite direction, and we will go into that, you know, but you can have acceleration, you can have a positive acceleration and a negative acceleration, and we're gonna I'll try and explain that in a very simplistic fashion. When an object slows down, okay, its acceleration is in the opposite direction to its velocity. And I think you'll get a much better understanding of these things when we represent them in a graphic uh, representation. Okay? So, again, you can have a positive acceleration and a negative acceleration. Okay? But when an object speeds up, its acceleration is in the same direction as the velocity. All right. All right. So you need to you need to have a little understanding of the Pythagorean theorem, because when you had vectors, you can do it, um, you know, two ways. Okay. Remember, when you have vector quantity is going to have magnitude and direction, and you can add them. You know, if I am traveling at a certain velocity due west, and then I turn uh, say northward, and I travel at a different velocity, and then I travel eastward at a different velocity, I can add all of those things up. I can add them up. You know, those are vector quantity, but I can add them up. And there is a special method to add those vector quantities. Okay, so we can add vector quantities using the Pythagorean theorem, or we can um, we can use the parallelogram theory to do that. But let's use the Pythagorean theory to add vectors. So adding two vectors that make a right angle to each other. So say for instance, okay, so if we have an object moving in this direction, straight up, and then we have an object moving in this direction. Okay, so we can get the resultant. Okay, so you you know you might move in this direction. Okay, and then you move in this direction, and then they ask you to find the resultant of that motion. So if an object moves upwards, say, give it a number, 2 feet, and then another object moves, say, towards the right, say 6 feet, you can add those vectors using the Pythagorean theorem, because these vectors make a right angle to each other. So we know the resultant is the hypotenuse. And then the Pythagorean theory tells us that a squared, the hypotenuse, is equal to b squared plus c squared. So you can get the resultant. So this will be the resultant vector. So if you're going to have a motion in, say, this direction and this direction, the resultant is a vector moving in this direction. Okay? So this is using the Pythagorean theorem to get the resultant of two vectors. All right? And again, you know, this is the hypotenuse, this is the opposite side, and then this is the adjacent side. Okay? So when you have two vectors that make a right angle to each other, you can get the resultant, and the resultant is the hypotenuse. Also, if you just think a little bit, so for instance, you have a vector. Say you have a vector that moves in this direction. Let me just draw that. All right, so you have a vector that moves in, say you have a vector that moves in this direction. Just, okay. So these are not isolated things now. These are, okay. Say for instance, you know, somebody is riding a bike and they move in this direction. Okay, they move in this direction. Say this is six feet. They ride in this direction in 6 feet. 6 feet. You can resolve this vector. Okay, you can resolve this vector. And how you resolve it, because each vector is going to have what we call a horizontal component and a vertical component. Okay, each vector will have a horizontal component and a vertical component. So what if you want to resolve this vector, you can get the horizontal component by just going up, and the horizontal component by going across, which is the same thing as this would be the vertical component, and this would be the horizontal component of this vector. Okay, so again, if an object is moving in this direction with a certain magnitude, you can resolve this to get the horizontal component of that vector, and you can get the vertical component using the Pythagorean theory again. Okay, because you know that this squared is equal to this squared plus that squared. Okay, so in that situation, you will know the hypotenuse, and you're not going to know this. So you use trigonometry principles to get the vertical and the horizontal component, and we'll show you how to use that. But you know, again, if you have a vector that moving in that direction and another vector that moving in that direction, you can get the resultant, right? Because once they travel, they make an angle of 90 degrees, then the hypotenuse is the resultant of these two vectors. And then the corollary is true if this is the direction of a vector. Okay, this is the direction of a vector. You can resolve this vector into its vertical component and its horizontal component. We're going to do a lot, because when you're doing mechanics, you have to understand this fully, because you're going to talk about you're going to have multiple motions, and you have to combine them together, and you have to have a very good way of combining them together that makes sense, make good scientific sense. So that is what, when we talk about vector addition, subtraction, that's what we're talking about. All right. So again, it will become more apparent once you understand what's happening. So again, if you have a vector that uh, say moves in this direction 12 feet and another one that moves in this direction 5 feet, you know, this is the resultant. This is the resultant of the two vectors, because these two vectors make a 90 degrees angle. Okay, so this is the resultant of those two vectors. So we can use the Pythagorean theory, which says that x squared is equal to 12 squared plus 5 squared, and then you solve for x. Okay, so x is 13, so the resultant is 13. So what we're saying is that if you have a motion in this direction going towards the right, and you have a motion going, say, downwards, this is the resultant of those two motions. Okay, this is the resultant of those two motions. Okay, and it's going to have a certain direction. This is the direction of that motion, and then the magnitude of that motion is this number. Okay, so vector addition allows us to combine motions. So this is not something in isolation. This, when you do any complex motion, you have to add the motions together. And vector addition is one way of doing it. All right, and another example: motion 6 feet in that direction, 8 feet resultant is x. Just solve for x, again using the Pythagorean theory. But as I said before, if you have a vector that moves in, say, this direction, say an object is moving in this direction, okay? It has a magnitude, it has a direction. There's always a vertical component and a horizontal component of this motion, okay? There's always a vertical and a horizontal component of this motion. So what you do, all you do when you have a vector, to get the vertical component at the top of it, you drop a straight line down, and to get the horizontal component, you go straight horizontal until you get to the tip of the vector. So this is the vertical component of this vector motion, and this is the horizontal component of this vector motion. Okay, you will know the magnitude of this motion, because that's what you're describing. You're going to know the magnitude of this vector motion. What you won't know is the vertical component and the horizontal component. This trigonometry ratio will allow you to solve for the vertical and horizontal component. The trigonometry relationship tells you that the sine of theta, which is this angle, is equal to the opposite side divided by the hypotenuse. Again, with a 90 degrees triangle, this is the opposite side, this is the hypotenuse. Okay, all right. So the angle is right there. So when you have the angle right there, this is the adjacent side, this is the opposite side, this is the hypotenuse. So the sine of theta, the sine of this angle, is equal to the opposite divided by the hypotenuse. So if you know the hypotenuse, you can calculate this side. You can calculate the length of the. So this would be the horizontal component of this vector. Okay. There's also another relationship. The cosine of this angle,
Okay.
or the cosine of any angle, is equal to the adjacent divided by the hypotenuse. So again, if it's this angle you're talking about, this is the adjacent, this is the opposite. So the cosine of this angle is equal to the adjacent divided by the hypotenuse. And then the tan of the angle, this is the angle, adjacent, remember if this is the angle you're talking about, the adjacent side is always right beside it. The opposite side is right there. And this is always the hypotenuse. Remember, the hypotenuse, this is the vector quantity that we know. We know the direction and we know the magnitude. We don't know the vertical component of this vector, and we don't know the horizontal component of the vector. But knowing these trigonometrical ratios, we can calculate the vertical component and the horizontal component. Okay? The tan of theta is equal to the opposite
Okay.
over the adjacent. So this trigonometry ratio will allow you to resolve your vector into its vertical and horizontal component. Okay, what we have here. So when we say S-O-H, the sine of the angle is equal to the opposite divided by the hypotenuse. So it's difficult to memorize these trigonometrical ratios, but if you know this is SOHCAHTOA. So sine of theta is equal to the opposite over the hypotenuse. The cosine of theta is equal to the adjacent over the hypotenuse. And the tan of the angle is equal to the opposite over the adjacent. In essence, you need to use this over and over and over until it sticks. But you will need it to resolve your vector. Okay? Because each vector gonna have a vertical and a horizontal component. So SOHCAHTOA. Okay, so just go over it. All right. So, and again, this is just a practical example. Again, if you know, say, all right. So a building. So this is a practical application. So just follow it closely. A building is 50 feet high. So 50 feet high. At a distance away from the building, an observer noticed that the angle of elevation at the top of the building is 41 degrees. So the building is 50 feet high. The observer, which is right there, observed that the angle of elevation of the building is 41 degrees. To the nearest foot, how far is the observer from the base of the building? So all right, so the building is 50 feet up, okay, 50 feet high. The observer notice that the angle of elevation, sorry, the the angle of elevation of the top of the building. So he's looking up to the building and realize that this angle here is 41 degrees. To the nearest foot, how far is the observer from the base of the building? So the observer is right here. So what you need to do is get the horizontal component of this vector. You want to get the horizontal component. Okay, so again, the observer looks up the angle of his elevation on top of the building, 41. You know the height of the building. What you don't know is how far he is from the base. But you can use trigonometry ratio to do that, because you want this number right here. Remember, tan of the angle. Remember the okay. So go back. SOHCAHTOA. So it's, in essence, what you're going to have to do is write down this little abbreviation, walk with it for, a few months, study it. Once you know it and you can commit it to memory, you can toss it away. So the tan of an angle, TOA, is the opposite over adjacent. So SOHCAHTOA. Okay? So the tan of the angle is so TOA. So it's the opposite. So this is the angle we're talking about. So SOHCAHTOA, TOA. All right. So the tan of the angle is equal to the opposite over the adjacent. Okay. So the tan of 41 is equal to the opposite, 50, over the adjacent, because this is what you need to know, how far he is from the base of the building. So the tan of the angle is equal to the opposite over the adjacent. So just rearranging the equation, x is equal to 50 over tan 41. You use your calculator and it will give you what tan 50 41 is. Okay, so you just use your special calculator. Tan 41 is less than 1, and you put it in the equation, and x is 58. So 58 feet. So the observer is 58 feet from the base of the building. So you should commit this trigonometry ratio to memory, but you're going to have to use it over and over and over. SOHCAHTOA. Okay, so sine of the angle is equal to the opposite over adjacent. Okay, cosine of the angle is equal to adjacent over hypotenuse. The tan of the angle is equal to the opposite over adjacent. So once you have the angle closest to it is the adjacent, this is the opposite, and the hypotenuse. You just commit it to memory and it will be fine. All right, so again, we're talking about the resolution of vectors. So when we talk about the resultant of the vectors, it is the sum of two or more vectors. When you combine vectors, or when you add vectors, the resultant is the sum of two or more vectors. And there's a special principle to add vectors. Okay, the component is each part of each part of a two-dimensional vector. Remember what I said, when you have a vector, you can resolve that vector into its horizontal and vertical component. Every vector can be resolved into its horizontal and vertical component. So when you do vector resolution, the process of determining the magnitude of the vector, okay, so the overall magnitude, again, you can use the parallelogram or what I just showed you, the trigonometry method. So, whichever method you want to use. So so let's look at this case. So you have a motion. So you have a motion that comes this way and then it goes this way. So any complex motion, so for instance, you walk into work. You're going to travel at a certain speed in a certain direction, and you might, if you plot it on the graph, it might look like this. You travel this direction, certain distance, and then this direction, certain distance. This is the overall, um, this is the resultant. So when you combine these two motions, this is the resultant. And this is the parallelogram method. So you you plot this motion, you plot that motion, you get the resultant, and you just complete the parallelogram. Okay, so this would be the resultant of these two motions. Okay, again, if there's a motion, if there's a motion that travels in this direction, uh, and then one travel in this direction, this would be the resultant. Okay, sorry. I mean, if sorry, you travel in this direction and then this direction, this would be the resultant. Okay, so you travel this in this direction, certain magnitude, and then you travel a different direction and a different magnitude. You can combine the motion, and then this will be the resultant. Okay, so again, you can use what we call the parallelogram method or the trigono or the Pythagorean theorem method. Okay, all right. So if if you look at this, there's a motion that you know this is one motion. Okay, you can see it has a certain direction and it has a certain magnitude. Remember what we said, the length of the line diagram tells you about the magnitude, and then the orientation is the direction. So this is one motion, this is another motion right there. Okay, this is the resultant. This is the resultant. If you if you just follow what I was saying earlier, this motion right here, you can resolve this motion into its vertical component and its horizontal component. Okay, so this is 90 degrees. This is the hypotenuse. So this squared is equal to this squared plus that squared. So you can resolve this vector into its horizontal component and its vertical component. And then also with this motion, you can do the same thing. Resolve it into its horizontal component and its vertical component. So when you're going to add these two vectors together, you're going to have their horizontal component and then you have their vertical component. Okay? You cannot add vertical and horizontal component. You can add horizontal component to horizontal component, vertical component to vertical components. So when you do that, so this is one motion, okay? It has its direction and its magnitude. You resolve it into its vertical component, its horizontal component. This is a second motion. You resolve it into its horizontal component, its vertical component. So you add all the vertical components. So the vertical components would be this right there plus this one. These are vertical components. Horizontal component would be this right there and then this right there. And then when you add all of that together, you get this, the resultant. So this is going to give you, because this resultant going to have a vertical component and it's going to have a horizontal component. So a fairly easy method in resolving or adding vectors is to, once you get a vector, get its horizontal component, get its vertical component, you're going to add all the vertical components together. You add all the horizontal components, and then you'll get the resultant. Okay? All right, so so vectors can be added using the parallelogram law. So when you use the parallelogram law, you join the vector tails. So tails to head, okay? So tail to head, and the resultant vector is the diagonal of the parallelogram. So so you tail to head, and then the diagonal is the resultant vector. So that is using the parallelogram method, but you can use this simple method. Okay, so this is one vector, this is another vector. Resolve the vector into its horizontal component and then its vertical component. Horizontal component, vertical component. You add up all the vertical components, then you get the resultant vertical component. You add up all the horizontal component and you'll get the horizontal component. Okay? So, all right. So what I'm gonna do is I'm gonna stop here, and then our next session we can do examples of vector resolution, because just talking about it and not doing it might be a little bit difficult. So um, I